Good afternoon, everybody. Thank you for being here. Today it's my pleasure to introduce you to Associate Professor of Civil and Environmental Engineering, Stefano Galelli. He did his bachelor, master's, and PhD at the Politecnico di Milano in Italy. Then he moved to Singapore, where he did a postdoc and then started a faculty career. And over 10 years you were in Singapore. Yeah, that's a long time. And then finally he left Asia and decided to come here to join us here at Cornell. So thank you.
Thank you, Ricardo. Thanks for the introduction. All right, so good afternoon. Before I even start, I have a question. How many of you have a background in hydrology or know anything about rivers? 1, 2, okay, great. So there are multiple reasons behind the choice of this topic, of what I'm going to talk about. So if for whatever reason you heard about me or you heard about my work, most of the work I do is in the space of water systems, power systems, and how they interact. Typically, vulnerability of water and power supply to the variability in climate. But there's another topic that I've been particularly interested in during the past 5 or 6 years, and this is in some sense tangential to my work, and that's the ability of understanding how river discharge changes over very long periods of time. And the reason for which we need to do that is to understand rivers better, and if we do that, we can also understand how the vulnerabilities, the water supply systems are exposed to changes over time. And you will see that there are essentially 2 pillars on which the process of reconstructing long-term series of river discharge builds. One is time series analysis, which I think is relevant to the system seminar series. The second one is the information that we can retrieve from proxies, for example, the information that is contained in tree rings. So today I'm going to talk a little bit about where the science of streamflow reconstructions is at the moment, what are the opportunities for time series analysis, and at the same time, what are some of the major limits that this field is experiencing as well. Okay, so before I continue, there are 2 important people I have to acknowledge. One is Dr. and hopefully soon to be Professor Hong Ngoyen. Is a former PhD student with me in Singapore. Now is working as a postdoc at Columbia University. The other person is Professor Brendan Buckley. I owe him a lot in terms of learning about the fields of tree ring science. Now, first of all, let me spend a few minutes talking about the process of reconstructing streamflow discharge from tree rings. So the first fundamental question is, why do we even care about it, right? And the very simple answer is because streamflow records are typically short. So what you see here is a visualization for 6 different continents of how long a streamflow time series is, right? So you can see, for example, that in Europe, on average, you might get time series that measure river discharge with a length of approximately 50 years or so. There are some interesting outliers, more than a century, but they're very few. The same roughly, but with the different empirical distributions, applies to North America, right? On average, again, you can work with probably 50 years of data or so. But that's not really enough, right? What does even enough mean? Enough typically means multiple centuries. And why is it so? That's because the behavior of rivers changes very slowly in response to climate forcings. So the longer the time series we have, the better it is. All right, now let me brag a little. This is work I contributed to, but the example I'm bragging about here is how good the time series we had to work with is. So this is a very rare exception. This is a time series that is 216 years for the major river in Italy. It's called the Po. And in 2022, we had in Italy a major drought. And what we were trying to understand at the time was to characterize the severity of that drought. And there's a big difference in doing that if you have 50 years of data or if you have 200 years of data, right? You can have a much better characterization of the drought. So what you can see here, for example, is a table where we ranked all the worst droughts in the past 200 years. These are the top 10. And in this specific case, the 2022 drought stood out significantly. You can see, for example, here, if you look at the return period, it approached a return period of about 600 years, right? But if you calculate those statistics with 50 years of data, the return period you're going to get is completely different, right? So this is perhaps hopefully enough for motivation. Now there are a few questions, right? How do we do streamflow reconstructions? When did we start doing them? Why do we care about them? Where are they done? And so on, right? So let me answer these questions very briefly. First of all, what is a streamflow reconstruction? How do we accomplish it? By banking on tree rings. So even if you don't have a background in hydrology, I believe that all of you, in one way or the other, have heard that trees grow rings, right? And the width of the rings changes with the hydrological conditions, right? In wet years, trees tend to go faster and bigger, right? So the ring width will be larger. In very dry years, the growth will be minimal, right? So the fundamental idea, and I'm going to leave it like that for the moment, is that if we can learn a mathematical function, imagine a simple linear regression model that maps rings to river discharge, then we have a way to reconstruct discharge back in time. And why is that? Because some tree species can live for very long periods of time. So in the best cases, you can work with trees that live for 1,000, even 2,000 years, right? So what's the process? Again, I'm keeping things simple for the moment. First, you want to learn the function, right? And you will learn this function over an instrumental period in which you have access to the tree rings as well as the river discharge observation. Let's say 30 years of data, 50 years of data, 80 years of data, right? Once you learn this function and you only have tree rings for another, let's say, 300 years, then you carry out this so-called reconstruction process. Okay, so now you go back in time and you try to reconstruct how the river behaved over a longer period of time. Now, when did we start to do this? To the best of my knowledge, the very first work was in 1936 in Nevada by George Hartman. We used tree rings to study the magnitude of droughts in the Truckee River Basin in Nevada. That was followed shortly after in 1937 by Howley's work that expanded this work to the eastern United States. And in 1945, this is a very important work by Schulman, started to assess the reliability of Hoover Dam for wartime production. At that point, Hoover Dam still plays a critical role, but at the time it was particularly important in 1945. But all these works are not really reconstructions on streamflow. They were more studies that were looking at relying on tree growth indices as indicators for wet and dry periods. The major change happened in 1971 with Stockton, and a few years later with Stockton and Jacobi, because Stockton and Jacobi started to use time series analysis technique that were also being popularized in the 60s and the 70s to do the very first reconstruction of streamflow. So mathematical functions that were mapping from climate proxies, in this specific case tree rings, to river discharge. Make sense? Okay. And since then, things have been flying. Where are reconstructions done? What you see here is a visualization of the geographical footprint of streamflow reconstruction. You can see, perhaps unsurprisingly, that a lot of work has been done in the Midwest, right? And you can explain easily with essentially two reasons. This science was started and flourished at the Arizona State University in Arizona. More broadly, there's a lot of work that has been focusing on the Colorado. The later work that you see in Europe and Asia, East Asia, South Asia, and Southeast Asia happened much later. We're talking more about early 2000s. That's fine. You can also see the starting century of the reconstruction. So you see that on average, we're perhaps able to reconstruct river discharge from about 1500s or so. That depends heavily on the species that you have available, right? Some trees live only 200-300 years, others live much longer. It also depends on land management. In a lot of places, unfortunately, primary forests that have been there for long periods of time have been cut. So we don't have access to those climate proxies anymore. You also see the work in Africa and South America has been limited. Most of the work in South America, for example, has been done in Chile. So I told you about the when, the why, the where. The why just a little bit more in terms of why do we really care about this, right? And the motivations initially were primarily to support water resources management. So this example here is more of a cautionary tale that an example is probably the best example I could give you. And this is related to the Colorado River Basin. What you see here are the upper reaches of the Colorado River, so southwest US. And what you see here is a reconstruction, it's a very famous reconstruction by Connie Woodhouse, David Mekong, and Stephen Gray for this point here of the Colorado River. So you see that over 500 years, of course, river discharge fluctuated significantly, but the key piece of information is this one. This period here, you guys see, from roughly 1910 to 1940 is the period during which the Colorado River Compact was drafted. For those of you that are not familiar with it, the Colorado River Compact is essentially the contract that negotiated how water from the Colorado would have been partitioned among 6 states in the United States, right? And if you look at this, you can easily see that those decisions were made during the wettest period of the past 500 years. So they decided to allocate water that on average doesn't exist in the river, right? Once again, speaks to the importance of working with long-term series of data when we are working with rivers, okay? And since then, in general, reconstruction can be used for many other purposes, but it's important to remember that the motivating need for reconstructing river discharge is water resources management. And the interesting to notice at the same time is that streamflow reconstructions are not really used actively by water resources analysts. One exception is Rohini, who's using it in her thesis, but on average, we don't see a strong uptake of streamflow reconstructions by the water resources analysts. And I think there are a few major challenges. Number one, the accuracy is problematic. So as I'm going to show you later, reconstructions are great, but they struggle in particular to capture the upper tail of the distribution. Why is that? Because of a saturating effect of soil. Once the soil gets too saturated, the tree will not grow more and more, right? So there's a non-linear, essential effect that is tricky to capture. Second, the format is not great. Reconstructions follow 3 rings. You have 1 ring per year. You have 1 data point per year, right? But a water manager would ideally like to work with, let's say, daily data, weekly data, perhaps monthly resolution, annual, you're really stretching it. Third, it's not always feasible to do streamflow reconstructions. I'm going to skip this in the interest of time. And fourth, typically water resources managers, engineers, environmental engineers, and so on are not really trained in this space. So today, because this seminar looks more at the systems aspect, I'm going to talk more about 2 aspects that can essentially be connected to time series analysis. A, how do we make streamflow reconstructions more accurate? And B, how do we improve their temporal resolution? Okay, so 2 aspects for this talk. So let's begin with accuracy. Okay, I talked about streamflow reconstructions, but I didn't really tell you how reconstructions are made. And the cornerstone of streamflow reconstruction is linear regression. As simple as that. Okay, so how does it work? I believe you're all familiar with it. You will have some climate proxies. In our case, we're interested in 3 rings, and when the output of interest is either the streamflow or some transformation, for example, in the log values of river discharge. Okay. In reality, things are a little bit more complex. It is true that linear regression is used, but it is also true that you don't just measure 3 rings and input in your linear regression. There's a lot of work that goes into creating proper time series that I'm not really covering today. Also, you don't carry out these measurements of 1 tree. You typically do it over dozens or trees or more. So there's also a essentially compression aspect or feature extraction or feature engineering work that has to be done, for example, using principal component analysis. So imagine that the conventional method is PCR, principal component regression. Okay? Now, if you use linear regression, you're going to have some problems. Of course, you bank on the assumptions of linear regression, but if you look at hydrological processes, typically there is no linearity that you cannot really capture properly unless you do some tricks, transform your input-output. The second is catchment dynamics. So there's memory within the system. Normally, a dry year can be followed, for example, by a wet year, but there's memory within the system. You can imagine that as a Markovian process. So capturing these transitions, for example, from one state to another, is a challenging process if you're banking on linear regression. So some of the work we did with Hung and then later with Brandon was, okay, why don't we still bank in some sense on linear system, but we try to make things a little bit more sophisticated. So what you see here is a state space representation of an Armax model, autoregressive moving average exogenous. You have a state transition equation, one here, and an output transformation function. So the input are still the Kramer proxies, in our case 3 rings. The output is still the streamflow. What we're trying also to infer is the system state, right? What is the system state? Imagine soil moisture, how much water is in the soil. If the soil is very dry and it's raining, you're not going to get a strong response in terms of discharge in a river. But if the soil is wet and it's raining, then the response of a river will be different, right? So those are the kind of dynamics that you try to capture using a dynamic model. Now, things get a little bit more complicated. Of course, you have a number of matrices that characterize the state transition equation, the output transformation function. And when you look at the overall problem, you essentially have 2 major unknowns, right? On one end, you don't know the system parameters. So you have a system identification problem that you need to solve. But the only thing we have are also the input and the output. We don't know the system state, right? That's not measured. So then you also have a state estimation problem, right? So how do you solve that? Well, you can think about fixing the value of the parameters, identifying the state, using a Kalman filter, for example. Then you fix this and you identify the parameters and you keep reiterating this process, right? So essentially the idea is expectation maximization or maximization expectation, right? So a EM learning framework, which is exactly what we did, right? So first step is you fix the value of the parameters, you do a forward pass with a Kalman filter to estimate the value of the system state, and then you can also do a backward pass to improve that estimation. Once you have a sense of what the value of the system state, the state trajectory is, then you can use maximum likelihood to re-identify the best value of the parameters. And then you keep iterating this process essentially until convergence, right? So let me show you how this works and what we can learn from it. The example I'm going to take are from Southeast Asia. As Ricardo was mentioning, I've been in Singapore for 10 years, so most of my examples are always indeed from, most of the time from Southeast Asia. So the proxies that we use is information retrieved from 3 rings that is already gridded for Southeast Asia. We're looking at roughly 800 years of proxies, meaning that we're trying to reconstruct the history of river discharge for 800 years. The areas we're interested in are a number of stations in the Mekong. The Mekong is the major river essentially of Southeast Asia, and the Chao Phraya in Thailand. And in the experimental setup, the bottom line is we have one model identified for each discharge station. The input variables are, first, we have this feature engineering process of doing a principal component exercise to remove collinearity, use cross-validation, of course, to get a sense of how robust the model is. And we learn a linear regression model versus a linear dynamical system model to get a sense of essentially what sort of improvements in terms of performance we can get. So this is an example for one river in Thailand, the Ping River. What you see here in orange is the instrumental record, so observed river discharge of roughly 80 years of data, which is pretty good for being in Southeast Asia. You can see the linear regression sometimes struggle. For example, here, tends to overestimate, and during dry, wet periods, sometimes it underestimates. But on the other end, a linear dynamical system tends to work better. And that is, my explanation is that this is largely due to the fact that at the same time you're learning the catchment state. So you have a proper characterization of the system state. For example, when the system is dry, the catchment is dry, the response tends to be to better capture the response of the model tends to better capture what happened historically. The same is true for wet periods. So skill metrics R square, I believe you're all familiar with it. KGE is the King-Gupta efficiencies used in hydrology. Just imagine, for the sake of keeping things extremely simple, that it gives you an indication similar to R squared, and the best value you can get is 1. Now, the values that you see here are not great, right? Even a better model has an average between the two measures of performance, or roughly 0.6. And that is typically what happens in Streamflow reconstructions, going back to the problem of accuracy. It's not so easy to reconstruct the behavior of a complex nonlinear dynamical system just by banking on information retrieved from tree rings. But I'll get back to performance later. In general, just to give you a brief sense of, this is not a seminar on climate dynamics, but let me indulge just a little bit on that. So each line that you see here is a different station. So this is a history of the river behavior of 12 different gauging stations for 800 years. To compare them, of course, you need to standardize. So what you see here is a Z-score, right? One river maybe in one point has a maximum flow of 1,000 cubic meters per second. Another one will have 500. So it's difficult to compare, which is why we use the standardized Streamflow or Z-score. And what you see is that they tend to behave in a fairly similar fashion. So for example, you can see the two droughts, the anchor droughts. For those of you that don't know what Angkor is one of the most important, if not the most important archaeological site in Southeast Asia. I think Tom Ryder was shot there, perhaps you ring some other bells. And there's a number of studies, a very interesting one published on PNAS 2012, if I'm not wrong. They link the demise of the Angkor civilization to two series of droughts, which have been coined the Angkor droughts. The strange parallel droughts is a drought that happened in Southeast Asia and North America, if I'm not mistaken, and that's why it's called the strange parallels drought. And there's a reason for which rivers, even if they are close to each other but not that close, tend to behave in the same way. And that is explained by the impact that oceans have on rivers' behavior. So what you see here, we just focus on one plot, is the correlation between the temperature of the ocean, the sea surface temperature, and river discharge. When it's negative, it means that there are some areas of the ocean that essentially negatively influence river discharge, positive, vice versa, right? And if we look at this specific region of the equatorial Pacific Ocean, that is the El Niño Southern Oscillation. In Southeast Asia, it tends to have negative impact during the negative phase of El Niño, and positive impact on river discharge, which is known as La Niña. And if you look at different periods of time, again, these are things we can do if we have reconstructions. We can see that this impact was not consistent across time. There were periods where the impact of El Niño was strong, periods during the impact of La Niña, for example, or El Niño, was weak. And we can only understand these processes in climate dynamics if we have Streamflow reconstruction. So this reinforces the need for having long-term series of river discharge. Now, I think I have roughly 10-15 minutes left. Let me talk a little bit about format, right? All this work I've shown you so far has a resolution of 1 year. And if you are a water sources analyst, you will typically want to work with, systems model that have a resolution of 1 day, 1 week, 1 month, right? 1 year makes things very challenging, right? So then the question is, okay, how do we make models with a different resolution? So this is newer work that we published last year, and I believe there will be a lot of work following, not necessarily from us, but also from other people. So I'm going back again to Southeast Asia. This is the Chao Phraya. There are 4 stations we're interested in. This is the one that I've shown you actually in the previous part of the presentation as well. But now we don't target the annual river flow, we target monthly. And that makes things challenging, right? So here's the thing. If you're working with 3 rings, you have 1 ring per year. There's not much you can do about it. And you also know there's a nonlinearity that 3 rings don't really reflect. When the soil is very wet, the tree will keep growing, but the growth saturates, right? So if you look at this from an information theory perspective, what you're missing is information, right? You need information from other sources. Make sense? So here's the idea. You can still use chronologies of ring widths, but you have to start banking on other types of information that trees can reveal. So it is true that the most intuitive information in terms of climates and dryness and wetness we can retrieve from a tree are the rings. But if you talk to a botanist or if you talk to a dendrohydrologist, the amount of information that a tree contains is amazing. The process is how do we extract it, right? So we were lucky enough to work with a few colleagues from China that are specialized on oxygen isotopes. So perhaps some of you know that you can use stable isotopes of carbon or oxygen to date, for example, different, for example, organic elements that you can find in the environment. You can do that with trees as well. The reason being is that when water flows from the roots to the leaves through the xylem of a tree, there's an exchange in the isotopic content of the water that is in the tree versus the water that is flowing within the tree. So you can measure that with the annual resolution. And the beauty of that is that oxygen isotopes are actually sensitive to the wet season flow. So now magically you have 2 different types of proxies. One that is sensitive more to dry season and the other one that is more sensitive to a wet period. So the idea is, okay, now we try to combine them in a linear or nonlinear model, trying to push the temporal resolution. Make sense? So what you see here is the network of data we had access to. So you have 1, 2, 3, and 4 points from which we managed to get these chronologies of oxygen isotopes. And there are many other types of information you can retrieve from tree rings, from trees, for example, blue intensity, wood anatomy, and so on. So I'll get back to that later. So now you have more proxies, more inputs. You have to build a monthly model. So this is the way we did it. Of course, there are other ways, but let me tell you about what we did. So now you don't have one output variable, right? One predictant. You have 12. You have the flow in each month plus the total annual flow. And you have the corresponding predictors. Why aren't the predictors the same? Well, during the dry months, you will probably bank more on tree rings. During the wet month, you will probably bank more on isotopes, right? And during shoulder months, transition between wet and dry and vice versa, you may probably rely on different combination of predictors. So you have different, essentially, subsets of predictors. Simplest way to do it, sure, we can think about a linear regression and solve this with least squares. The problem if you do that is that you're going to have 13 independent models, so you have no guarantee that the sum of the flow in these 12 months is equal to the total river discharge. So you're going to have a stream reconstruction that is not accurate in terms of mass balance. Make sense? And that is pretty bad because it means your stream reconstruction is not really reliable. So the way we addressed this was to, okay, why don't we think about, for example, a penalty? Right now, what you have here is the sum of the predicted river discharge on a monthly time step minus the total annual river discharge, right? And you want to make sure that delta is as small as possible. So if you plug this back into your least squares, what you essentially come up with is a penalized least square. You can find penalized least squares, in general, penalized loss functions for many time series analysis problem like lasso, for example. And you have a way lambda that essentially gives importance to how concerned you are about this, right? If lambda is equal to 0, you go back to simple least square. So if you don't take any log transform, for example, of the output, there's an analytical solution to this, which makes the entire regression problem simpler because you still have the problem of picking the predictors of interest. If you switch, for example, to the log space of the output, then you need to use, for example, some sort of gradient descent method, for example, for estimating the value of the parameters. But if this works, you can actually have monthly reconstruction, which is pretty cool. So the setup, again, Southeast Asia, 4 stations in the 4 discharge station in the Chao Phraya River Basin. These 2 are particularly important. These 2 are the 2 main reservoirs in Thailand. If those of you, somebody has ever heard of the major floods in Bangkok during 2011, the role that these 2 dams played was pivotal. So getting, again, a sense of how rivers behave in the region is very important. We have 13 models per discharge station because you have monthly models plus a total annual model. You still have a variable selection problem because you need to pick up the predictors of interest. We use a genetic algorithm. I'm not going into the details of that. If you're interested, I'm happy to chat about it. Again, k-fold cross-validation to get a sense of how accurate the models are. If you do k-fold, in these cases, you have to pay attention. You cannot randomly pick. You need to keep at least 13 consecutive months in your k-fold cross-validation scheme in order to make sure you're making a fair comparison. So what do you see from this plot? Pretty much nothing. It's you have 4 rivers. You can see that models tends to agree. What I would highlight here, you have 4 different metrics of performance. R square, RE, and C are used more in the domain of dendrohydrology, is your coefficient of error and the other error. They both look at the ratio between the sum of the squared errors normalized versus the benchmark. In one case is the average river flow during the calibration, and the other one is using the validation period. C tends to be a little bit stricter in terms of metrics. What you see is that because you're banking on a larger amount of information, model performance tends to get much better, even if now we're at the monthly resolution. Is it all great? No. There are months or specific years, so I picked a couple of years where something odd happened that we're not really able to capture, even if we're using more information from trees. For example, 23 and the year 2000 had the major typhoon. At the beginning of the season, they caused this bimodal essentially distribution during the wet season, and we weren't, of course, with the trees. The trees are not responsive enough sometimes to what's happening within the environment to give you all the information you need if you're working at a monthly time step. Let me skip this, and let's now look at what we can learn. Now, you still have 4 rivers. SSI is a streamflow index, and to calculate a streamflow index like this one, you need monthly data. So this is with the number 6 here is related to the fact that you're working with a 6-month moving average. So you can do this if you have monthly resolution reconstructions. If you have annual, like pretty much almost everything that is been done so far, you don't really get to do that. And again, you can see that rivers tend to behave most of the time in a similar fashion. You can pick up a number of droughts. For example, this was the Victorian Great Drought. You have the strange parallel drought again, the East India drought. With the specific trees that we work with, in this case, we couldn't go back 800 years, like in the previous work I've shown. These are roughly 250 years, but with monthly resolution, not annual. But the other important thing is that you can pick wet periods much better as compared to other types of annual reconstructions. There are other things you can do. Now, you don't have 1 point per year, you have 12. So you can get a much better sense of what happened every different year. So again, you have the 4 rivers. Now, what we did was to color essentially the driest and the wettest year. So you have a much better characterization of water availability at any given point in time. And another interesting thing, this is very important for water management, is understanding the peak season starting month. So let me explain. In Southeast Asia, as well as other places, you have essentially a dry and a wet season, right? This is when the monsoon happens. This is the pre-monsoon period, the dry season, and the dry season. So from a water management perspective, knowing when the monsoon starts is super important because that's when you decide how much water to allocate for the wet season. So the monsoon starts in April versus June makes a big difference from a water management and electricity management perspective as well. So now because we have all this data with a monthly resolution, we can try to get that. There are algorithms that essentially allow us to label and determine when the monsoon started. So each dot that you see here is a year and is colored by how wet or dry that year is. So you see that there are rivers like the Nan that are very consistent. The wet season, the monsoon essentially always starts in July. You have rivers that tend to be less consistent, and you can also see, for example, here for this river and this river as well, that the later the monsoon season starts, the drier the monsoon will be. So that has a double implication from water resources management perspective. Now, let's wrap things up. I'm almost out of time. So I began this talk by talking about barriers that prevent the uptake of dendrohydrological data, Streamflow reconstructions in particular, to water resources management. Did we overtake them all? Not at all, but I think there will be some exciting developments in the years to come. Accuracy is problematic. The cornerstone is and will be probably principal component regression for a long time, but there's work on Bayesian linear regression frameworks, the linear dynamical system I'll show you, and other work that is trying to push that aspect. From my point of view, the most interesting one is though the fact that we don't really have to work with ring width only. Something that the dendrology community did much better in the water resources one is to create a good database. So the tree-ring global database has data very well kept for all trees, tree chronologies, anybody can go and download. As we go forward, we're getting more data also from many other types of proxies. That makes it a very exciting data mining, time series analysis, system engineering, if you will, problem, because you have great data you can work with, and that can help us push both accuracy and format. At the same time, there's work on stochastic generators. I think, again, Rohini, I keep mentioning your work, but you did great work in there. There are temporal disaggregation algorithms that can use to push format as well. I didn't really talk about unfeasibility or reconstruction, but this is something I prefer to skip at the moment. It requires perhaps a deeper discussion. And I believe as we do that and more work is published in this domain, I think there will be more uptake also in terms of learning about this in the water resources management domain. So with this, I think I'm 1 minute ahead of schedule. So for once I was good in keeping up with time. I'll stop here. Thank you for your attention. I hope you could follow perhaps more the math part than the hydrology and climate dynamics part, but I'm happy to answer any questions.
We have plenty of time for questions for Stefano.
For the dynamic systems, when you did the Kalman filter and then linear regression and like kept iterating,
Yeah.
Is that type of iteration process going to always converge, or do you have issues where sometimes it gets on the wrong track?
No, on the wrong track, no. So if you use expectation maximization, you have guaranteed the likelihood function will not get worse. It can stagnate a little though. So so it can be computationally challenging, that I admit and acknowledge. The main reason is that you try to do that with different initializations, number one. Number two, you have these big proxies of tree rings, these big networks, and you have a variable selection problem. You cannot feed all the input data that you have, let's say 500 chronologies from a tree ring network, because otherwise you have a poorly defined problem. So you have essentially a variable selection an outer variable selection problem, then you have an inner system identification problem. So you have to solve both. If you do it for one station, it's not too much of a challenge. If you do it for many different stations in a river network, then it becomes computationally challenging. So we move this to a big server. Yeah, you're welcome. Yes?
How's your use of tree rings to analyze how rivers flow over time very interesting? Do you know about any other organisms that are studied in the past to track natural phenomena in a similar way?
Yes, yeah, absolutely. So there's essentially an entire field that is called paleoclimatology. And that's essentially the process of reconstructing past climate using information that we can retrieve from climate proxies. So just to give you some examples, one is ice cores. So you can essentially, by the way, we don't cut any trees to do this work. I didn't mention that, but what you essentially do, you probe the tree with something that is roughly, let's say, alpha centimeters, more or less. So you extract a carrot essentially from the tree. The trick is you have to go exactly to the middle because that's where the first rings developed, right? You can do the same with, first of all, you do it with ice, and that is great to reconstruct information on temperature and CO2 concentration. So when you see plots, they show CO2 concentration 5,000 years ago, right? Where does that come from? Typically it's from ice cores. Another very important one are sediments on the bottom of lakes. With those, you can go back hundreds of thousands of years. You don't have annual resolution anymore, clearly, right? The temporal resolution gets much coarser. Another cool one that we haven't used yet, but we will, is corals. Corals contain a lot of information on sea surface temperature, because the way a coral grows, bleaching phenomena, etc., they're also related to the temperature of the ocean. The temperature of the ocean has also a big impact on the hydrological cycles and on rivers. So all the field of paleoclimatology essentially banks on speleotherbs as well from caves. You can go back hundreds of thousands of years. So all of that is important because climate models that we use for future projections are typically validated otherwise on just 50, 60 years of data, right? But if you're able to reconstruct air temperature for 5,000 years or 1,000 years, or you have information on CO2 concentration, then you're able to test these models on longer periods of time, which make them also more acceptable for the way we run them in the future.
Do you think that these models are becoming more inaccurate because of anthropological activity being more of a factor, or
which models are you referring to?
the paleoclimatological models?
No, not really. When it comes to rivers, the challenge that you have is that you're linking two natural phenomena, right? How much water you have within the soil, essentially, how the tree grew, and you try to relate that to how much water you had in the river, right? So it's easy, and that's the point I didn't talk about. It's easy to do that if the river is in pristine conditions, right? If a river catchment has been heavily affected by the construction of dams, agriculture, urbanization, etc., then those processes are disrupting the natural link between rainfall, temperature, and river flow. So you have to discount that before you learn your model, right? So you find a lot of benchmark work in the Colorado, because in the Colorado there are some sort of accepted ways of discounting the human efforts impact from the time series. So a lot of people use the Colorado, right? But if you're working on a river where you know that there's an impact, but it's difficult to remove that, essentially that effect, then it's a little bit challenging to use these techniques.
Do your regression outputs also give uncertainty bounds, and how big are they compared to the estimates?
Yes, you can get uncertainty bounds, so we do. So we have a couple of packages for these two techniques we developed. They can be, especially on annual reconstructions, they can be fairly large. But I think it makes more sense to communicate uncertainty rather than say it's a deterministic reconstruction. Bottom line is you're reconstructing how much water was, let's say, on average in a year or in every month in 1500s, right? So can you claim that you have 100% knowledge of that? No. Expressing that as a fully deterministic outcome, you're taking a big leap of faith. If you add uncertainty, it makes more sense, and the uncertainties can change also with time. For example, dry months, March in Southeast Asia is very dry. So the error you're going to get there is pretty small, even if you're reconstructing 300 years ago, right? But as you move to the shoulder months of the monsoon, or the beginning of the monsoon, or the monsoon itself, there can be a fair amount of uncertainty. Yes?
So I have a question about the precipitation proxy and the runoff proxy. Yeah, Streamflow proxy. So which one has more uncertainty? Do you know?
Second?
Which one has more uncertainty when we compare the Streamflow proxy to the precipitation proxy? Not proxy. I mean reconstructed value. So we can reconstruct the Streamflow with tree links, and we can reconstruct the precipitation through sediment core or something like that.
Yes.
So which one have the more uncertainty? It seems that stream flow can be affected by the naturalization issues. So,
Yes.
Yeah.
Good question. So yes, you can reconstruct precipitation. There's a lot of work done there. Absolutely. I think that there are a few different factors that can affect that. So I would say it depends on the location. So if the location comes, for example, primarily from storms rather than larger scale systems like the monsoon, you can have some difference there. Depends on the tree species, whether that specific tree species is a better proxy for stream flow rather than rainfall. So I think for the moment I would need to go back and read, but my answer is probably, I think it depends on the specific case. So there can sure be instances in which reconstructing precipitation is better than reconstructing river discharge, and vice versa in terms of accuracy. So it's a nice way of saying I don't know. I would need to look into that. Yep.
Thank you for your interesting presentation. Because all of the rivers you've been studying are in a similar geographical area, have you looked at including spatial statistics at all as predictors in the regression models?
For example?
Wouldn't there be some correlation between river discharges between rivers in a geographic area, and have you used those correlations and prediction variables?
No. So is there a correlation, spatial correlation? Yes, absolutely. We did not explicitly account for other predictors that can help us account for that, because those predictors would be available only for the instrumental period. For example, land use or other variables that can explain how a given river behaves in a confined region, because they would only be available during the period in which river discharge was measured. So they can help us have a better model for the instrumental period, but then when we want to go back in time, we can't bank on those anymore. So we essentially let the tree speak for themselves.
Yeah, so for the streamflow reconstruction, is there any impact of size of river? So streamflow, I think okay, it's relatively small, but what if it's a really big river?
So you mean if a larger river can be better predicted?
Or worse?
Or worse? Very good question. No, not necessarily. I think there are two factors there. One is which trees you're working with and how they respond to soil moisture. So that's one thing. The second factor is what kind of, so it's the proxies that determines everything. So if the tree responds well to climate forcings and the signal is picked up properly in terms of ring width, that's the typical one we work with, or other proxies, then you can have a decent streamflow reconstruction, I would say, regardless of how big or small of a river is. If it's an extremely small river, then I think things will become challenging, because then the response of the river may be not really related to our tree group in the past. And the other thing is observation measurements. Sometimes measuring river, we never measure river discharge. Most of the time what we measure is the river height, how much water you have, how many meters of water you have. Then you have some information about the cross section, right? So area times heights will give you flow. And the information about, the bathymetric information about the river, especially the cross area section, is not extremely reliable when you go back 20, 30, 50 years, because rivers are dynamical systems, right? They move sands, for example, or sediment sand can be mined from a river. So when you look at the Mekong, 60,000 cubic meters per second, the peak flow, is it 65, is it 55? You don't really know, right? So when rivers become extremely large, especially during peak season, there's fair amount of uncertainty in the actual observation itself. So I think those are the two main factors that play a role in how accurate reconstructions can be.
One last question.
Yeah, thank you. So, when you use the multiple linear regression,
Yeah.
I think you use the least square error
Yes.
estimation. But what if you use the orthogonal regression or something like that? Because it seems that the input value also have kind of error here, true ring estimation can have the error. So would it affect your result? I mean, in my case, yeah, it affects. So I just want to
Okay, and what would you suggest to use? I just didn't catch that part, sorry.
So, orthogonal regression. When you do linear regression, when we make the cost function, we use the least scale error. But
Yes.
we can also use the orthogonal projection.
Oh,
Yeah.
but you mean in the predictors?
But for the cost function. So when
Okay.
we make the cost function, we just get the residual in the y direction, but we can also consider the error toward the this line, orthogonal direction.
Okay, I see. Good question. It's something I haven't tried, so I can't really comment on that. In general, the common practice in this domain is to work more on the predictors, so to have more of a feature engineering exercise. So if you have 24 predictors, for example, typically what you would do is to run a PCA, a principal component analysis, cut that to, let's say, 10 orthogonal predictors, and then from those work with a subset of 3 or 4, which you know are already orthogonal. So that eases a little bit the calibration process later. Right, makes sense? But you can also do that within the learning process. It's just something I haven't explored. All right?
Let's thank Stefano again.
Thank you.